Here we go. First thing we need to talk about is polarity. And then after polarity, we talk about intermolecular forces. And then we need to talk a little bit about covalent versus ion properties of covalent versus ionic compounds. Yes, Brenda. Yeah. Carter, can you do that? Like completely off? Like that? You guys are good taking notes in the dark like this? All right. Okay, so here we go. We're going to start with polarity. And the idea of polarity, we kind of started getting to it last week when we were talking about the shapes of molecules and the electronegativity difference. You guys remember that? Where we had, say, we had an oxygen, and we had a, let's put a carbon on here. Okay, and here's our bond. And if our oxygen here has an electronegativity of 3.5, and carbon is 2.5, if I'm not mistaken, that means the electrons want to hang out around the oxygen more than they hang out around the carbon, right? Okay. Well, this effect happens for every bond. Every bond in every molecule has something like this. Now, if they're equal to each other, then they're equally shared. But if one of them has a greater value here, then it's going to hold on to the electrons more than the other one. So it's just sort of you can use these values to help shape where the electrons are around the molecule. Well, sometimes you get to, well, once you have a whole molecule, like, say, hydrogen, like water. Okay, and oxygen is going to have its two lone pairs over here. And oxygen is so electronegative compared to hydrogen that almost all of the electrons, just a little bit of time around the hydrogen, little bit of time, and then a whole lot of time around the oxygen. And that makes this end over here negative in general. It's kind of a negative end to it. And over here we have a positive end because on this side we have these two protons sticking out because the oxygen's hoarding all the electrons. Yeah? Okay. This creates what's called a dipole. I don't like that color. This creates a dipole. Okay, and a dot. What do you think di means here? To pole. Okay, it has to do with polarity or the pole on. So there is a positive pole and a negative pole on the molecule. When this happens, these molecules can start to attract to each other. And when this happens, this is what creates intermolecular forces. That our hydrogen, I'm just going to be real quick with how I draw it here. Okay, so our hydrogen molecule, I'm going to make a few copies of this. There we go. Okay. That we know this negative end here, that the hydrogens represent the positive end, and that the oxygens are the negative end, and so we can start making when we have a whole bunch of these molecules, they'll start stacking on each other, and they'll be attracted to each other. That the positive ends will be attracted to the negative ends, and we'll have these forces that are attracting each other, these Coulombic law attractions, right? The electrostatic attraction. Okay, we'll pull these molecules together. Okay, and this is an intermolecular force, and in particular, intermolecular forces involving hydrogen are called hydrogen bonds. They're called hydrogen bonds. And these hydrogen bonds are exceedingly important in the nature of water. Most of water's properties are so special because of these hydrogen bonds. It's one of the reasons why water expands when it freezes, because this relationship creates this crystal structure, and I don't have a good way of drawing it, because it's 3D and I don't draw it that well. But I'll show you guys and/or upload a video that demonstrates it really well. However, this doesn't necessarily just happen with hydrogens, okay, or water. It can happen. This sort of interaction can happen with other molecules that don't have hydrogens, and so we'll do NF3 here, and so that's going to look like nitrogen has a nitrogen is this light blue color. And most halogens we draw as green. So it's going to be one back here. Going to be one in front. There's going to be another one back here. Okay, and then there would be a lone pair of electrons up here. Okay. What shape is this, by the way? Not tetrahedral. Tetrahedral would be if we have another atom up here. Yeah, this is trigonal. Trigonal. Pyramidal. Pyramidal. Trigonal, pyramidal, or pyramidal. But with a nitrogen-fluorine bond, nitrogen has electronegativity of, like, what, oxygen is 3.5. I think nitrogen is 3.0 for nitrogen. And fluorine is 4.0. So where are all these electrons going to be? They're going to be by all the fluorines, right? Okay, and so that means this end down here is going to have this negative charge. And even though there's a couple of electrons sticking out, this is kind of going to have a positive charge over here. Even though this pair of electrons it has a negative charge, the other end is so negative that this end's more positive. You guys follow me there? Yep. Remember?
Less negative.
Okay, this end is less negative than this one. So this will have a more positive. If it's less negative, it's more positive. So because of that, here is a molecule that doesn't have hydrogen in it, but it would be polar. Okay, and so this would have a dipole. This would have a dipole interaction or a dipole-dipole attraction. Okay, it is weaker stronger, and down here is weaker. A dipole interaction is weaker. Okay, and the big reason is hydrogens. When you take when you're sucking the electrons away from a hydrogen, you're left behind with a naked proton. It's naked. Okay, it's just or the other way I call it, it's a zit. It looks like this giant positive pimple on your molecule. It's just this. The protons are sticking out there, and it's naked, and it's ugly, and it has no electrons shielding it. And so it's a highly positive charge right there. And it will be very attracted to any other polar particle that's out there that's got a negative end to it. So that's why hydrogen bonds are very strong. Hydrogen bonds are why water takes so freaking long to evaporate. And I want to do a demo here, hopefully, in a little bit to show you guys that. Maybe we'll do it tomorrow. If you put, like, say, rubbing alcohol and water on a table, which one evaporates first? The alcohol, right? Because alcohol is significantly less polar than the water. And so the water molecules stick together and they hold on to each other, and it takes a lot of energy to break that to break that attraction apart. You have to pull on them harder in order to get these molecules apart, and then that's when they fly away into the air. Alcohol, it's much, much less. And so it'll evaporate first. It takes less energy, less heat energy to get that up into the air. Then you get stuff like, hold on. Then you get carbon dioxide. Carbon dioxide has this bond would be polar over here. And it would also be polar over here. But it would be balanced, right? That this side would have the same number of the electrons would kind of look like right? So not so many electrons around the carbon, all the electrons around the oxygen, but it would be on both sides. And if it would be equal, if the electrons are equally distributed throughout the whole atom, this, what do you think we call this one? If this one's polar, what do you think this would be? This is a nonpolar. It doesn't have poles. Both ends are negative. It doesn't have a positive or negative side. Okay? Well, because of that, nonpolar molecules are going to have really low melting points, also known as low. You can't see this? Oh. Okay. Okay. They have low melting points and low freezing points. Okay. And the funny thing is that these are actually the same. At what temperature does water melt? 0 degrees Celsius, yeah? At what temperature does water freeze? 0 degrees Celsius. Okay, freezing and melting are just different directions through the same temperature point. You're going this way, it's melting. You're going this way, it's freezing. Okay. It's the same thing with boiling point. Okay, those are the same. They're low because they're not, the molecules themselves aren't attracted to each other. But you guys see situations where this is you guys seen frozen carbon dioxide before. You guys know what that's called? Yeah, that's dry ice. You guys seen dry ice before, yeah? Okay, you put it into the water and it bubbles up at Halloween. You get the cool looking punch or whatever. How does that happen?
Because carbon dioxide freezes.
It just takes less heat.
How do nonpolar molecules stick together enough to form liquids or solids?
Because they're bonded by carbon.
Okay, and this is the weakest of our forces. I'm going to move back over here. Something we know about electrons. Electrons move randomly in their orbitals. Okay, remember the shapes of the electron orbitals that we drew are regions of space where we would find the electron 90% of the time. But where an electron actually is in any particular moment could be anywhere, pretty much anywhere in that orbital. Well, if you take that over time, that the chances of this being exactly equal at any particular moment is really slim. Sometimes you'll have a 60-40 split in the electron, in where the electrons are. Like, for just a moment, you might have 60% of the electrons over here and 40% of the electrons over here. On average, it's a nonpolar molecule. But because electrons move randomly, there's times when it's not. In those moments, those electrons are attracted to each other and then they move away. I equate it to when you guys are going through, like you're in the mall or something, or you're at a place where there's a lot of people, and you walk past someone and they're wearing something that smells very nice. Yeah? And you walk past and you have this, ooh, and you lean in a little bit, and then it's gone, and then you keep moving. Yeah? And so it's, these two ships that pass in the night, but you're walking past and you smell each other, and then you kind of, and then, no, it's not like a sniff, okay? But you catch a whiff of something, and oh, that's nice. For me, it's Victoria's Secret Pink. That's the one that just, I know that one. That smell is just like, ooh, I like that smell. What? I apologize for being open with you guys. I should keep that information to myself. It's okay. What I'm saying is it's real, and you guys have all experienced this. You guys have all experienced the smell. It's like, ooh, I like that. Okay. Okay. But what would happen if the two people that had these smells, if the smeller and the smell, the smell emitter and the smell detector, okay, were on bicycles moving past each other? Would you necessarily catch that smell?
No.
It'd be over so fast that it wouldn't deflect your path. Okay, so we carry that over here, that this momentary attraction, this whiff of each other, okay, occurs when we have this imbalance in electrons. But the only way it really affects the motion of these molecules, or the way it becomes intermolecular force, is if they're moving slowly. It only affects slow-moving molecules. Okay, but it's this effect that when the molecules start getting slower and slower, this effect starts to take a larger and larger effect. And that's how we can get things like dry ice. Because we cool it way down, we make the molecules move slower, and then they can start being attracted to each other. That's how we can get things like liquid helium and liquid hydrogen. Because those are very nonpolar molecules, but they're so cold that these electrons, the way they're dispersed around the nucleus, will start attracting to each other only if they're that cold. These are called, there's two names for these. They're called dispersion forces. Also known as van der Waals. Yes, there are two A's. And these are the weakest. These are the weakest of the intermolecular forces. So which one was the strongest? The strongest intermolecular force was hydrogen bonding, which came from polar molecules that had hydrogens on them. The next strongest was our dipole interaction. Okay. And then the weakest, which came from polar molecules that don't have hydrogens on them. Okay. And then we have nonpolar molecules that experience dispersion forces that do kind of attract each other a little bit, but it's a very weak force. Okay. All right. So that brings us to the third thing, which were covalent versus ionic. Covalent versus ionic properties. All of those molecules we just talked about only occur with covalent compounds. Only covalent compounds will experience intermolecular forces. Ionic compounds don't, because they are crystal lattices and they don't make molecules. Ionic compounds do this. Now I'm just going to do it one color for right now and try and go with size. But okay, it's hard to do the second layer on it. But the idea is that it alternates every other, your ions will alternate based on their composition formula. Okay, so like NaCl. Okay, just a second more. Okay, NaCl, there's one Na for every Cl, right? And so they'll make something like this. But then you can get like magnesium chloride, where you would have one magnesium and two chlorides would be attracted to it, and then it would have its own lattice that's attracted in the same way. These lines right here are not they're not covalent bonds like the lines in the other one. These are direction of attraction. That this is attracted to that because of what? It's an ionic bond, so what keeps ionic bonds together? No, not polarity. Polarity only exists with, well, no, I take it back. if you were to have a sodium and a chloride together, it would be extremely polar because you would have a negative ion and a positive ion. Yeah? Why are these two ions attracted to each other? What bonds them together? We need to remember this word. Electrostatic attraction. Okay, this is opposites attract. This is the official term for positive and negative charges attracting each other. Lamar, question. Forces.
Direction of what?
Of attraction. It's the direction. So when you see a lattice, the lines in between are just, there's attraction between a positive and a negative ion, a cation and an anion. Okay. The electrostatic attraction is the strongest of the bonds. Ionic bonds are the strongest of the bonds. Ionic compounds therefore have high melting points. Because there is a transfer of electrons, the ions, when you put them in, say, water, okay, they will dissolve and they will get attracted to the high polarity of the water molecule. Okay. And because of that, you now have charges in the water moving around freely. And because of that, ionic compounds will also conduct electricity. And they dissolve. But they're not the only things that can dissolve. There are nonpolar things that can dissolve also, but generally not. All right, covalent compounds. Okay, they form molecules. Okay, and the molecule is an individual unit of the covalent compound. If you're a Star Trek fan, it's like the difference between an individual spaceship and the Borg. Okay, ionic compounds are the Borg. You will be assimilated. You just create a larger part of a lattice and the crystal grows. Okay, covalent compounds, you have individual little molecules, and if you don't know who the Borg are, your parents haven't raised you right. Okay. Covalent compounds then, in contrast, have lower melting points. Okay, and they do not conduct electricity. They're called insulators, but you don't need to know that name. Something that doesn't connect to electricity is called an insulator. So that'll do it.